In the previous class, we established a general form of the electric or magnetic fields for a wave that is traveling in any arbitrary direction, which need not be along either of the three axes, because that's how most waves travel and that is the normal case. And moreover, we are mentioning that we have been doing this for a reason, that instead of now trying to think that the wave is traveling along either of the axes, let us reserve the use of the axis to denote the boundary of two media, and for that we have to analyze how the waves will behave as they try to travel from one medium to another medium. So we had seen, to have a quick recap, we had seen that the electric field for any arbitrary direction of movement of the wave, or propagation of the wave rather, we said that the electric field E is some E0 as a vector form, where the unit vector denoting the direction has now been absorbed in this E0 bar. So it is the magnitude as well as the direction. Now this times the phase notation, that is e raised to minus j k dot r. So, or rather, if I'm not wrong, it is r dot k, but it's one and the same thing. So we had seen that similarly for the magnetic field, it comes out to be something of this kind, where the directions of E0 and H0 are perpendicular to each other. We had seen that, but the notation is slightly changed in the sense that the unit vectors of either E or H are now absorbed in the first constant. So now, well, it need not be constant, but just the magnitude component. So what we had proved in the previous class was that this phase phi, or the dot product r dot k, is essentially the product of the phase constant and the distance, which gives rise to the space phase. So that is nothing but beta x cos phi x plus beta y cos phi y plus beta z cos phi z. We had defined that the phi x, phi y and phi z are the angles which the direction of wave propagation makes with the three axes, and the cos terms for each of those angles are also called as direction cosines. So we had discussed this in the last class. Now, when we talk of a wave trying to travel from one medium to another medium, as we mentioned this in the last class also, that recalling our school physics, we know that phenomena like reflection and refraction do happen. Well, for example, when you have a wave traveling from air to glass, we see refraction. When a wave is traveling from air to a very shiny metal, we see reflection. So in some sense, the movement of a wave from one medium to another medium can also be thought of moving along a transmission line and then hitting a load, or going from one transmission line to maybe another transmission line, which is different in nature. But that is sort of taking the easy route. Not all aspects of transmission line will help us understand the phenomena, because now we are no longer concerned with what is happening along only one dimension. We are now concerned about the behavior of a wave in 3D space. So So let us take an easy example, or rather the most direct example of a wave traveling from medium 1 to medium 2, where both are dielectrics or perfect dielectrics. So without losing generality, let us denote the x-axis, or rather the xy plane, as a media boundary. The xy plane is a boundary between medium 1 and medium 2. The second assumption, again without the loss of generality, let us assume that the wave is moving along the xz plane. So the wave lies entirely on the xz plane. That is its direction of propagation along, or I should not say the word moving, I should say propagating. The fields can be in any direction, that's a different thing. So let's suppose the plane on which the wave is propagating is the xz plane. So let us now define or draw this axis. If this is the medium 1 on the left hand side and this is medium 2, so what we are saying is the xy plane is the boundary. So let us define this as the positive x-axis, and somewhere over here let us assume that y is coming out of the plane of the paper. Now this notation you are already familiar with. So that means the y-axis, positive y-axis, is coming out of the plane of the paper. And that obviously leaves us with the right hand thumb rule. If you take x and y, so this would be the positive z direction. So just for the sake of simplicity, I will show this to complete the figure. Now this we have taken. So somewhere over here the xy plane, which is a wall and the boundary is sort of existing along the plane which is perpendicular to the plane of the paper. So the xy plane is the boundary between medium 1 and medium 2. Now what are the characteristic properties of medium 1 and medium 2? So if both are dielectrics, that means sigma in medium 1 is 0. Likewise, sigma in medium 2 is 0. There is absolutely no conductive element. Likewise, we can say that let the medium have some permittivity epsilon 1 and some permeability mu 1. Here also I can define the permeability to be epsilon 2 and the permeability to be mu 2. So because for a dielectric these two are the characteristic properties. Mu in general largely stays the same across most of the media unless they have some magnetic properties, but let us not get into that for now. So if there are two media, in general they can have epsilon 1 mu 1, epsilon 2 mu 2. Now our second assumption is that the wave is propagating along the xz plane. So what is the xz plane? The xz plane is the plane of the paper. So let us assume that a wave is moving this way. How the fields are there? They are not either normal coming out of the paper or existing this way. That is implicit. So supposing if you say that this is the direction of propagation. So if the electric field exists along or coming out of the plane of the paper, then the magnetic field must be this way on the xz plane. So that is how our definition of wave fields are. But let us not get into that much of detail for the time being. So we are saying that let this wave be traveling and it hits the media boundary at the origin. So this is our wave, which was happily traveling along what it was thinking was a infinite medium. So now it hits the boundary. So how do we analyze this? So now without worrying so much about what the fields are, using direction cosines, we can write the E field or the H field in this format, where the direction of E and H are absorbed into the magnitude components. So since the nature of E and H look very similar, we can represent both of them using a common vector or field vector called as F, where F may be equal to E, F may be equal to H, that is a different thing. So because both of the nature of the E and H fields, we have now put them in a very similar fashion, we can represent them using one quantity, that is F, the field vector. It can be the E field, it can be the H field. For the time being, it is not important. So now if I am calling this as a vector F, or this is the way the wave is propagating, or rather the field is existing and the wave is propagating this way. This is not the F vector. So the wave or the field can be written in this way. So I should say F existing. So we can say that this wave, since it is hitting the boundary, it is the incident wave, or I should say it this way. So let us call this wave field as Fi, that is the incident field. So using this, I can write it as Fi0 vector. Now what this vector is, again, it's not of my concern at the moment because it will show you the field direction. What is more important is the exponential, because that tells us the wave direction. So this is E raised to minus j times this phase. Now in medium 1, I can say that the wave is propagating with a phase constant beta 1, which is nothing but omega under root mu 1 epsilon 1. And if at all there is any wave in medium 2, we can say the phase constant is beta 2. We have not said anything about the wave in this medium, so that we will see. But before that, let us put this assumption. Well, one thing we know is that the phase constant of this wave in medium 1 will be beta 1. So the space phase for this field Fi will be given by the beta, the xyz, and the direction cosines. So let us write it down. So the incident field that is Fi vector, which is Fi0 times e raised to minus j beta 1 x cos phi x plus beta 1 y cos phi y plus beta 1 cos phi z. Now let us try to investigate what these are. These phi x, phi y and phi z. So for that let us redraw the three axes. This is the x, the y is this way and z is here. So if the wave is hitting at the origin, let us suppose the angle of incidence it makes with the normal to the surface, because the surface is now, or the boundary surface is perpendicular to the plane of the paper. So the normal will be defined, or the incidence angle will be defined on the plane on which it is traveling. So let us call this as some angle theta I. So with this, let us try to find out what is phi x, phi y and phi z. So what is phi x? Phi x is the angle the wave propagation vector makes with the x-axis, the positive x-axis. So if you look at it this way, the angle which this wave makes with the positive x-axis will be pi by 2 minus theta I. Simple geometry. If it is, you are thinking it is traveling this way, then the angle over here will also be theta I. So this angle will be pi by 2 minus theta I. Now what is the angle phi y? That is the angle the wave propagation vector makes with the positive y-axis. What would that be? The positive y-axis is this way. So the angle between this pen and the plane of the paper is pi by 2. So phi y is pi by 2. And phi z is the angle this wave makes with the positive z axis, which is nothing but theta I. So that means cos phi x will be cos of this quantity, which is sin theta I. Cos phi y will be what? Cos of pi by 2, which is 0, and cos phi z will be cos of theta I. So therefore I can write using these the incident field on the boundary this way times this beta 1 I can take common because it is the same for all terms. Only what will change is the direction cosines. So for the x-axis I will have x sin theta I. The y component will vanish because it is 0. Z will be, so the z component will be z cos theta I because of this. Well, this is what the incident wave looks like, or let's say the incident field. So now the field is happily, or the wave is happily traveling and it hits the boundary. So what will the incident field now be at the boundary? So at the boundary, what can we say? At the boundary, in general, now let us suppose that you are not considering origin to be the only point where the wave can hit. In general, we can also have a wave like this which is hitting some point, same angle. I can also have something of this kind. So it can hit different points along the x-axis. But now we can say that at the boundary, since it is orthogonal to both y and z, the y and z are both 0. So at the boundary, let us say, we'll call this at the boundary. So now what happens is, if we put y is anyway 0, so what is happening is that at the boundary z also becomes 0 and this term in the exponential disappears. So therefore I can rewrite the incident field at the boundary, that is Fi is nothing but Fi0 times, so where we put z as 0, e raised to minus j beta 1 x sine theta I. That's it. This is what the incident field looks like. So now let us investigate what happens. If this is the boundary, let us see what this field causes. So if I want to see how the field is varying in magnitude, or the field is actually varying with time and position, I can take the real part of this field, and what I will get is nothing but this vector times cos beta 1x sine theta I. So if this is the x-axis along the boundary, what we see is the moment the wave hits, the nature of the field sort of exists like a sinusoid along the x-axis. So effectively it becomes something of this kind. So let us say this is the point at which it hits. So you have a maxima at this point. So if the sort of the wave hits this point with an angle theta I, what can we say? The moment the wave hits, some kind of a field disturbance happens on the surface because of this quantity. Some kind of a field disturbance happens on the surface. Now, if we were to sort of think in a different way and say that, okay, let us not care about what is the incident wave on the surface. We are more interested about this disturbance. Now suppose I am looking at the surface with a magnifying glass or scrutinizing the surface, and I am seeing that this kind of a field, or rather this kind of a field disturbance is happening. Now with this, can I then say that if there is a field disturbance, two things can happen. Either it is produced by a wave, or if I already have a field disturbance, this field disturbance can produce another wave. So now, if you are observing from medium 1, where the wave is nothing but the direction of the pen, this way, it is hitting the surface. So the person who is sitting on medium 1 and observing the surface from this side says that, okay, now my wave which is hitting the surface is the aggressor, or it is causing the surface disturbance. Now suppose somebody else is sitting on medium 2. The person sitting on medium 2 has no idea of the wave at medium 1. He is just saying that there is a surface disturbance in the form of a field variation which is existing both sides. So he will say, okay, I can see a field variation. So this field variation will produce a wave. And he will say that, okay, if now this wave is traveling somewhere, let us say along this side with the same angle, let us say theta I, you will see that essentially a similar phenomena will happen over here. So if you write it using direction cosines, you will see it is very similar. So effectively, it can be caused by a wave either here or here. So the person in medium 2 will say that, okay, now if a wave like this was incident on this surface, a very similar field variation would have happened, disturbance. But then this fellow sitting in medium 2 is very smart. He said, I know that a wave which is incident like this could have caused the same gradient, but the fact of the matter is there is no wave here. This wave is not there. So he puts the responsibility on medium 1 and says that you now have to make a wave which in medium 1, because you played smart by making a wave which is incident on the surface from medium 1. So now you have to make another wave which will do the task of medium 2 had the same wave come over here. So therefore a wave exists over here, and that is called as a reflected wave. So ideally you will see that these two angles are equal. So we are trying to be cheeky by looking at the laws of reflection which we studied in school, but in a slightly different perspective. And that we are trying to analyze by looking at this disturbance at the surface. Now let us forget about this for a moment. Let us see that there is some field which is existing at the boundary, or let me use a new page so that you don't get confused. Let us look at this from a little different angle. This is the boundary. This is medium 1 and this is medium 2. Mu 1, epsilon 1, mu 2, epsilon 2. So suppose this wave strikes the boundary. We already know that at the boundary we have this incident field vector Fi, which can be either electric or magnetic field. Now go back to the boundary conditions. We say that the fields at the boundary of two media must be continuous. So the tangential components of E field will be equal to each other, so on and so forth. The normal component of the displacement density will be continuous, like that. And so similar for the magnetic field. Now let us assume that this wave has some electric field component Ei bar and magnetic field component Hi bar. We know that this medium has an intrinsic impedance eta 1 that is nothing but mu 1 by epsilon 1. Intrinsic impedance or characteristic impedance, whatever you may want to call. Now this is nothing but, so this eta 1 is nothing but the ratio of the modulus of the E and H field vectors. Very good. Now what about medium 2? There will be some intrinsic impedance eta 2, which is mu 2 by epsilon 2. So because at the boundary the fields must be continuous, let us say that there will be some wave which is going over here with field components Et bar and Ht bar, where T stands for transmitted into the other medium. So what's going to happen is that the Et bar mod by the Ht bar mod will be equal to eta 2. Now eta 1 and eta 2 need not be equal. So therefore the boundary conditions, I can say that if eta 1 and eta 2 are not equal, then in general the Ei, Et, Hi, Ht also need not be equal. Because to satisfy these, if the wave is getting in here, independently in the two media, it should satisfy these two conditions. Now if you remember, let us say that the wave is somehow coming in to the second medium and it is traveling. Now it does not care what is on medium 1, but for medium 2, for the wave to propagate in the medium 2, this condition must be satisfied. But eta 1 and eta 2 are not equal. So therefore, this puts us in a problem. We want the boundary condition to be satisfied. For the wave to transmit from medium 1 to medium 2. But since the etas are not equal, the fields by themselves need not be equal. So therefore, to satisfy the boundary condition, some additional field will be induced back in medium 1. So, and this induced field, both E and H, which is induced back in medium 1, also comprises a wave. And this is the induced wave to satisfy boundary conditions, where we can say that the sum of fields because of the incident wave and the induced wave will now be continuous with what is the transmitted wave field. And this induced wave is what we call as the reflected wave. So the real reason behind having reflections, when you look at your face in the mirror every morning to get ready, what is happening is the reflection is happening because the metal is shiny. The mirror is a shiny surface, but effectively the reflection is happening because of the two media trying to satisfy the boundary conditions of the fields. Now forget mirror. We are now discussing two dielectrics. Consider two dielectrics, air and glass. Now we know that glass as such is not a reflecting surface. Now assume that you are standing somewhere in the evening and you are standing near a glass window. Which is overlooking something outside that room. And since it is evening, you have switched on the light in your room. Now, when you go very close to the glass, or even if you don't go close, you may see that you are able to see what is outside the window also. But at the same time, you are also able to see your own reflection. This is happening with glass also, in spite of the fact that glass is a transparent object. It's a transparent medium. So ideally, what we learnt in school physics is that transparent medium, ideally there should not be any reflection, but there is. And this phenomena for reflections between two dielectrics was investigated by Freshner. So this reflection is also called as Freshner reflection. And Freshner reflection is defined as reflection at the boundary of two media which are dielectrics. If you have not seen this phenomena happen before, that if you stand in front of the glass and see your own reflection, please try it out today evening. So now let's get to business. Let's get to business. So without losing generality, let us go back to this definition. This is the x-axis, this is the y-axis, and this is the z-axis. So let us say the wave is incident, making an angle of theta I with the normal. The wave gets transmitted and makes an angle theta t with the normal. And let us say the induced wave or the reflected wave makes an angle of theta r with the normal. Right? So in general, this field or the incident wave will have this field Fi, the reflected wave will have the field Fr vector, and this will have the Ft vector, which is the transmitted wave. Now let us write the field vectors using direction cosines. F for the incident wave, we already know it is nothing but x sine theta I plus z cos theta I. What about the reflected field or the field of the reflected wave? We can write it as some Fr0 vector times e raised to minus j beta 1 because it is medium 1. In medium 2 it will be beta. So here the direction cosine will be again the angle which it makes with the positive x-axis is pi by 2 minus theta r. So it will be x sine theta r, and the angle which it makes with the z direction, positive z, is pi minus theta r. So this will be minus z cos theta r. What about the transmitted wave vector? It will be ft0 e raised to minus j beta 2, because now we are talking of the transmitted field. This is the boundary. Times it will be x sine theta t. What about the z component? The y component for all cases will be 0 because they are orthogonal. This will be plus z cos theta t. I hope I have got it correct. Yes. This is the angle which it makes with the plus z axis. So it will be this. Now, if I say at the boundary, x need not be 0, but y and z will both be 0. So what we can say? We can say that Fi vector becomes nothing but Fi0 plus Fi times e raised to minus j beta 1 x sine theta I. Fr vector will be Fr0 times e raised to minus j beta 1 x sine theta r. And the Ft will be Ft0 times e raised to minus j beta 1 x sine theta t. This is at the boundary. Now, at the boundary, what is the condition? The tangential components of the fields must be continuous, because we know that Et1 should be equal to Et2 and Ht1 should be equal to Ht2. There is no concept of a surface charge or surface current right now. So the tangential components of the boundary fields will be like this. So the tangential components, these are absorbed in the F0 vectors. So we can rewrite and say that the tangential components which are parallel to the surface grazing the surface. So what would that be? So just to rewrite, this is Fi tangential is nothing but, we can just write this Fi0 tangential e raised to minus j beta 1 x sine theta I. The reflected component tangential will be very similar, but sine theta r, and the transmitted field tangential component will be this minus j beta 2 x sine theta t. So as per boundary condition, the net tangential field on medium 1 must be equal to the net tangential field on medium 2. So that means the tangential component sum of the incident and reflected or the induced field should be equal to the field that is transmitted. So if I now apply this, what I'll get? I can say that the Fi tangential plus the Fr tangential must be equal to the Ft tangential. So substituting, what do we get? We get, if you substitute these big expressions, Fi0 plus Fr0 sine theta r will be equal to Ft0 times e raised to minus j beta 2 x sine theta t. So what is the solution for this equation? This equation means that two things should happen. The phase components, or rather, the phase components of these two must be equal, and this should be equal to the phase component on the right hand side to maintain the continuity of the fields across the medium. So therefore I can write beta 1x sine theta I will be equal to beta 1x sine theta r. This is one. The other is either of these phases must be equal to this. So I can say beta 1x sine theta I will be equal to beta 2x sine theta t. This is equation number 2. From equation 1, what do you see? This gets cancelled. So from this you see theta I is equal to theta r. So this proves the law of reflection. The angle of incidence is equal to the angle of reflection. But point number 2 is little tricky. We are saying beta 1 sine theta I is equal to beta 2 sine theta t. Let's understand what this means. So if I am writing beta 1 sine theta I is equals to beta 2 sine theta t, let's substitute what is beta. Beta is omega under root mu 1 epsilon 1 times sine theta I will be equal to omega. Remember, the frequency does not change. Mu 2 epsilon 2 sine theta t. Now assume that mu 1 equals mu 2 equals some mu. That is a very valid assumption. So in that case, we are left with this equality. Epsilon 1 sine theta I is equal to root of epsilon 2 sine theta t. So if I rewrite and cross multiply, I will get sine theta I by sine theta t will be equal to under root of epsilon 2 by epsilon 1. Does this look familiar? Does this look familiar? Yes, it does. This is nothing but the refractive index as per Snell's law. This is the refractive index. So this is also called, this ratio is also called refractive index of medium 2 with respect to medium 1. So to satisfy the boundary conditions, we are seeing so many things happening. The wave is bending, that is refraction, and the wave is also inducing some field back in the medium 1, that is the reflected wave. So today we have proved the basic laws of physics or optics that we studied in school, that is law of reflection as well as refraction. So with this, we saw that proving this in a more rigorous manner using the field theory. So this is what we saw today. We shall continue from this point on in the next class. Thank you. So the discussion about establishing the laws of reflection and refraction was majorly about the wave which is traveling in a particular direction and is incident on a medium boundary or the boundary between two media. So we just assume that there was a direction. We never said much about the direction of the individual E and H fields. So let us take a look at that. So let us say this is the positive x direction, and as we had taken the convention, this is positive z and y is coming out of the plane of the paper. Now we had said that the wave is incident in this fashion, making an angle of incidence theta I with the normal. So now we know that if the wave is traveling this way, then the E and H fields will definitely be perpendicular to the direction of propagation. So let us say if the E field, let us consider at this point on the wave, if the E field is coming out of the plane of the paper as a special case, since this is the incident wave, let us call the E field vector as EI. Then what will be the direction of the H field? Simple, you have to use the right hand thumb rule. If the thumb direction points towards the direction of propagation, then the curled fingers must go from E to H. That means the H vector will be along the XZ plane. So this is HI vector. Simple, the cross product of E and H will give you the direction of propagation. Now this case has a very special name. If the electric field vector, let us assume it is linearly polarized, and it is polarized in such a way that it is only exists along vertically over the plane of the paper, this is called as perpendicular polarization. In general, waves can be elliptically polarized, they can also be circularly polarized, but we shall limit our discussion to linearly polarized waves because they are the easiest to understand. And the best thing about the linear polarization is that the electric field maintains its orientation no matter which point you are on the field or on the wave. So now we had discussed that there is a reflected wave which is flowing in this direction with the same angle theta I, and a transmitted wave with angle theta t. We had already proved that the angle of incidence and the angle of reflection are equal, thereby establishing the law of the reflection. So now for this reflected wave also, let us mark the field directions. Let us first go for the E field. Now how will the E field behave? So if the incident E field maintains its perpendicular polarization, it will come like this. Notice that I am pointing the pen outward of the plane of the paper. That is how we have taken the convention for E. So if it comes this way, it will hit the boundary. Now with respect to the boundary, this E field is a tangential field. So the tangential field will be continuous. So over here also in the transmitted wave, I can directly say that the moment it crosses the boundary, I will also get a field that is coming out of the plane of the paper. So therefore even here the direction of the ET vector will be coming out. So obviously the HT vector will be this way. So because of this direction of the E field, the tangential field will preserve its nature and in general will also be perpendicular for the reflected wave. So therefore if I draw over here, I can say even this field in general will be perpendicularly polarized. So what about the H field? The H field will be in this direction. So I should name this as HR and this will be ER. Sorry for the... So the H field will now be looking this way, perpendicular. So in general it can be going into the plane of the paper also, the E field, but let us not talk about that. Let us say that in general they are vertically polarized or perpendicularly polarized. So maintaining the boundary conditions, what we can see is that because of the boundary conditions, the incident wave, the reflected wave and the transmitted wave, all of them will lie on the same plane. So this is the other law of the reflection as well as refraction. So let us just write the field equations which we derived already. So for the incident electric field, the EI will be EI0 times e raised to minus j beta 1 times some direction cosine. Likewise, ER will be ER0 times e raised to minus j beta 1 times some direction cosine, and the transmitted field ET will be ET0 e raised to minus j beta 2 times the direction cosines. Now I am not writing the direction cosines primarily because now I am interested in what is happening at the boundary. So at the boundary, at this particular point, we have x equal to y equal to 0, which is also equal to z. Since we are considering the origin point, or rather than saying at the boundary, I should say at the point of incidence. At the point of incidence, it's the origin. So all of these will become 0. So needless to say, the exponent for all these e terms would become 0 and essentially this would become 1. So what we had established as a result of the boundary condition is that the tangential electric field on the left hand side and the tangential electric field on the right hand side must be continuous. So applying the boundary condition, the net electric field on the left hand side is because of the sum of the incident and reflected waves, and that on the right hand side is because of the transmitted wave only. So what we get essentially, this term essentially vanishes. So we get EI0 bar plus ER0 bar equals ET0 bar. So now at the boundary or at the point of incidence, we need not treat these as vectors. We can simply recall from our discussion on the boundary conditions that the magnitudes must also be continuous. That is EI0 plus ER0 equals ET0. So the tangential fields are continuous. Now let us rewrite this slightly. Let us divide this whole equation by the incident field. So if I divide this whole equation by EI0, what I will get is 1 plus ER0 by EI0 equals ET0 by EI0. Now what is this term? This is the reflected field by the incident field at the boundary point of incidence. So this indicates reflection coefficient, which is very similar to V minus by V plus at the load for a transmission line. And what about this? This is the transmitted field divided by the incident field. So this is called as the transmission coefficient. So since we are talking of the perpendicular polarization, let us define the reflection coefficient as gamma suffix perpendicular. And the transmission coefficient we can define as tau suffix perpendicular. Since we are dealing with perpendicular polarization. So what now can we say? We have established the relationship between the reflection coefficient and the transmission coefficient using electric field. So if we rewrite this equation, it will be 1 plus gamma equals tau. Or if we rewrite, this will be tau minus gamma equals 1. So the question is, can we find out what this reflection coefficient and transmission coefficient are? But we have one equation with two unknowns. So let's call this as equation 1. Let us now try to hunt for the other equation. So the first equation we got by applying the boundary condition for the electric field. So the second equation, like that, we can get by looking at the boundary condition for the magnetic field. So now comes the fun. What will be the equation for the magnetic field? So if I now redraw this, so if I look at the magnetic field vector, if you recall, it was something like this. Let us redraw this. So for the incident wave, Hi was like this. The reflected wave, the HR was like this. This is the incident, reflected, and the transmitted, the HT was like this. So what we can say? We can say that as we approach the boundary, you will see that the H fields are all oblique. So therefore we need to see what is the tangential component of these fields. So tangential component for the Hi would mean the projection along this axis. So if this is theta I, what will be this angle? If this is theta I, this will definitely be 90 minus theta I. So this angle will be theta I, because this is a 90-degree angle. Similarly, for the reflected field, we are taking the projection along, let us say, this direction. So here also we must take the projection along this direction. So what can we say about this angle? This is theta I. So this will be 90 minus theta I. So this will be theta I. So this component for the incident wave will be Hi, or let us say so the component over here looking downwards, since the component is existing over here along the upward direction, we can call this as minus HR cos theta I. And over here we can again take the projection along this direction, and it will be ht cos theta t. So at the point of incidence, the direction cosines will all nullify, and the tangential field on the left hand side will be an addition of these two. So we will get hi0 just like how we got for the in terms of the ei0 and er0 and et0, we will get in terms of hi0 also. So hi at the boundary will become hi0. So that is hi0 cos theta I minus hr0 cos theta I will be equal to ht0 cos theta t. This is the equation for the boundary condition for the tangential component of the H field. So now we already know the relationship between E and H of individual waves. So the relationship between the, if this is the E vector, Ei, Er and Et, the relationship between the magnitudes of the fields is related to the intrinsic impedance of the medium, which is eta1 for medium 1 and eta2 for medium 2, as we've discussed. So this we can write as ei0 by eta1 cos theta I minus er0 by eta1 cos theta I, and that will be equal to et0 by eta2 cos theta t. So again, if we divide this equation by ei0, what will I get? I will get cos theta I by eta1 minus cos theta I by eta1 er0 by ei0 equals cos theta t divided by eta2 et0 by ei0. Now these two terms we have already defined. This is the reflection coefficient and this is the transmission coefficient. So rewriting this, we will get the following equation. And that is, we will get cos theta t by eta2 tau plus cos theta I by eta1 times gamma is equal to cos theta I by eta1. Now this is my equation number 2. We had already gotten equation 1, which is like this, and now we have got the second equation, which is also in terms of tau and gamma. So now very easily we can solve these two equations simultaneously and we can find out what is tau and gamma. So I will write those for you. I have already solved them and I shall not solve them over here. So you can verify this later on yourself. So gamma is actually equal to eta2 cos theta I minus eta1 cos theta t divided by eta2 cos theta I plus eta1 cos theta t, and the tau for the perpendicular polarization is given as 2 eta 2 cos theta I divided by the same denominator eta 2 cos theta I plus eta 1 cos theta t. Is that clear? So what do we observe? What do we observe? If the two media are dielectrics, we can say that eta 1 and eta 2 are real for dielectrics. So if eta 1 and eta 2 become real, the cos terms will always be real. So for dielectrics, the reflection coefficient as well as the transmission coefficient are equal. Sorry, are they real? Sorry, they are not equal. They are both real. So what can we say again? If eta 1 and eta 2 are real, can we correlate this discussion with transmission lines? Yes. If I have a lossless transmission line that is terminated with a real load, in that case also the reflection coefficient at the load will be always real. Remember, these are reflection coefficients and transmission coefficients at the boundary. So now the load can be thought of as a boundary between the line and the end. So what other things can we say? So we can say, by looking at the nature of gamma, theta I and theta t, they are always limited to 0 to pi by 2, because that is the range of the incidence angle, the reflected angle, and the transmitted angle. So because of this condition, all the cos terms will be positive. So therefore, I can say that the magnitude of this gamma will be less than or equal to 1. So as we know, the value of reflection coefficient is always less than 1. You cannot reflect back more than what you are transmitting. But what about the tau factor? The tau factor can be more than equal to 1 or less than equal to 1. Both are possible. So what does this mean? If it is more than 1, are we transmitting more than what we are making incident? Well, are we? So I leave this to you as a food for thought. Prove or disprove this statement. Transmission coefficient being more than 1 in magnitude means we are sending more power into the second medium. So think on this as an assignment. So now, so far we have analyzed for the condition where the nature of the E field is perpendicular to the plane of the paper. So now let us take the second case where the E field vector lies on the plane of the paper, or it's parallel to the plane of incidence. So what we call as the parallel polarization. So we have this X. Now I shall analyze this much faster than the earlier case. This is Z, and if you assume that a wave is incident at this point, This is the y-axis. The angle which it makes is theta I. The reflected wave angle is also theta I. The transmitted wave makes the angle theta t. Now, let us assume that the electric field vector is now this way. So it is somewhat parallel to the plane of the incidence. So the electric field vector has to be always orthogonal to the direction of propagation. So let us say it is this way. So we can say, if we mark this as EI, now where will the magnetic field lie? Where will the magnetic field lie? So again, use the right hand thumb rule. The direction of propagation is this way. So the magnetic field will now come out of the plane of the paper outwards. So this is HI. For the reflected wave, I leave it to you as an exercise. What we will now do is this tangential field will come over here and the same boundary conditions will be preserved. So even over here, the magnetic field component will come out of the plane of the paper, or it will be vertical. So in such a case, you can easily prove that the electric field for the reflected wave will be in this direction because of the right hand thumb rule. The wave is now propagating this way. Over here, there will be not much change with respect to the incident voltage or the incident wave. So what we now have is HT will preserve its direction of polarization and the E will look like this. So with this is the direction, right? So now very easily you can prove that using the boundary conditions, you can prove that HI0 plus HR0 will be equal to HT0. This is the first thing, and using the H field components, you can prove that EI0 cos theta I minus ER0 cos theta I will be equal to ET0 cos theta t. I am not getting into the proofs of this. You can do it as an exercise similar to the way we did for the perpendicular polarization. So you can do this out by yourself. So again from here, if we define the transmission coefficients in the parallel case and the reflection coefficient in the parallel case, this is not 1, 1, this is parallel. So again we can say this is ET0 by EI0 and this becomes ER0 by EI0 at the point of incidence. At the point of incidence. So from these you will get two equations. I will directly write them for you and leave the details to you as an exercise. And now you can prove that the first equation will be tau parallel divided by eta 2 minus gamma by eta 1 equals 1 by eta 1. This is the first equation. And the second equation is cos theta t times tau plus cos theta I times gamma is equal to cos theta I. And this is the second equation. Now you can again solve these pair of equations simultaneously and you will see that the reflection coefficient gamma now becomes eta 1 cos theta I minus eta 2 cos theta t divided by eta 1 cos theta I plus eta 2 cos theta t, and the tau, the transmission coefficient, will be 2 eta 2 cos theta I divided by eta 1 cos theta I plus eta 2 cos theta t. So what you will see is that the nature of the reflection and transmission coefficients are very similar and can be correlated very easily with what we found in the two cases. One is the parallel polarization, the other is the perpendicular polarization. So now let us take a small example. Let us say, suppose the wave is incident normally. Normally means what? Vertically along the boundary. So if this is the boundary, the wave is incident normally. That means theta I and theta t are 0. So what will be the gamma in case of the parallel polarization? This will be eta 1 minus eta 2 divided by eta 1 plus eta 2. In case of the perpendicular polarization, which we derived earlier, what do we see? It will be something very similar, but it will be eta 2 minus eta 1 divided by eta 2 plus eta 1. So essentially same, but with a same in magnitude but with a minus sign. So now does this remind you of something? This is very similar to the transmission line ZL minus Z0 divided by ZL plus Z0. So only difference is that which way you are now looking for. So if I say that look at two transmission lines, one having impedance eta 1, the other having impedance eta 2. So at the boundary of these two lines, which are lossless, if you are going this way, the reflection coefficient will be what? Eta 2 minus eta 1 divided by eta 2 plus eta 1, because at this point the wave has not yet reached the end of the line. So the impedance it will essentially see is the characteristic impedance of the line. Or if the wave is propagating this way, the reflection coefficient is nothing but eta 1 minus eta 2 divided by eta 1 plus eta 2. So this is the way to sort of draw a correlation between the two. So this is the idea which I wanted to put. So not only have we analyzed how the fields behave after reflection or refraction, we have seen that they obey the laws of reflection and refraction, which we have proved. We also examined certain cases of polarization of the wave, whether the E field is vertically polarized or whether it is horizontally polarized. So that is the case of the perpendicular and the parallel polarization cases respectively. So we shall continue from this point on in the next class.